rectangular forging, and today we will cover the rectangular forging. So how do you find the analysis? So let me show you the slab analysis. So we will make a slab and see how many forces are acting on it. We will also learn about the little bit about yielding criteria. Remember, we went over the yielding criteria, Tresca and von Mises, maybe in our first lecture. I think I went over this in my first lecture or the second lecture. Let me double check. E Fluids review, mechanics review, casting, fluids review. Yeah, this was my first lecture. This is the power law for stress strain curve when you are doing plastic deformation, and when you are doing the average extrusion stress, you take the average of that stress and then you find out the required stress to pull the wire through the die. This is the average stress. And then we will go over the Tresca and von Mises one more time in our lecture. I'm just reviewing. This is the von Mises stress that it says that distortion energy, when it is very high, then material starts yielding. And how high it should be, that this is our criteria. So sigma flow should be equal to uh, the stresses should be 1.15, the yielding stress. If that is the yield, that is the amount, then the material will start changing its ductility. It will go into the deformation process, you see. So, and usually when we have restricted one dimension and we are doing the uh, dimensional stresses, so what happens that when we have no strain in one direction, you see there is no strain in this direction, because um, it is restricted. Only the depth changes and the width increase. Then we have the yields criteria and the font misses, and this is our Tresca. Tresca is it says that the material will start flowing when this stress, this is the k mean general constant, any constant, you see. And I'll just explain to you. There's a more stress circle, sigma max, sigma min, and this is the average. And this is like a what? This is radius. Radius is equal, if this average stress, which is sigma max minus sigma min, this is suppose zero line. Okay, suppose this is a zero line. Sigma max minus mix sigma min divided by 2. If that is equal to the k value, any k constant only, okay, if you achieve that stress, then material will start shearing. That's the Tresca says. Okay, we will go over this again in our lecture 4. So this is the slab analysis. I will pick up a slab and do some stresses and share some uh, assumptions. Forging is plastically deformed, perfectly plastic. Friction coefficient mu is constant, all sliding to start with. Plane strain, no z direction deformation. So one dimension is restricted. This is our um, assumption in any thin slab. So we will use the von Mises criteria. Okay, please draw this diagram with professor. Open your notebook. Okay, so let's do some analysis here. So I'm gonna show you. Look at this. This is a slab. This is like a complete forging. It's a complete rectangular uh, piece which we want to forge. Okay, height is reduced and width is increases. In the forging analysis, this our uh, compressive force from the forging force. It's known as a forging force. And what will happen? You see, this is a center line. Okay, this is our center line, and I'm taking this portion on the left side. So let me show you. Let me show you over here. If I remove this slab, which is for analysis purpose. So this is our coordinate, x coordinate. This is my y coordinate. This is my z coordinate. And in the z, we assume it does not change per unit depth. Okay, the depth does not change in its forging process. Only the y reduces, x increases. The width increases, the height reduces. Okay, so let me show you. Over here, we assume this is the forging force pressure. So, and then over here, when this material moves outward, this is the stress also here. Stress is different here, and this is my pressure, applied pressure. So the friction force is opposing the flow. So friction force is mu times the applied pressure. So this is a force. You know, pressure equals to force per unit area. Agreed. So forging force equals to pressure times area. And you will ask me, Professor, what is area? In this case, look over here. This is my width. So if I take consider this is my width, uh, total width, and this is my depth. Okay, the whole depth. So this is the like everywhere the forging force is coming everywhere. Okay, the whole depth is under the forging force. You understood this point? So that area is pressure times that area is under the forging force. You understood this logic? So you will multiply. In the end, you will see this is very important. In the end, you will be required to find out the forging force at the end of this analysis. I'm jumping towards the analysis end. So we want to find out the forging force required to change. Suppose if I say from 1 inch to 1/4 of an inch, reduce the height 1/4. So that reduction, how much force is required? So in order to do that analysis, so what you have to do, you have to apply certain uh, sigma forces. All the forces, they are equal to, in the x direction, they are equal to 0. So let's see, if this is the stress, and this is my height. Okay, this is my height, and you will say, Professor, why did you not take depth? So we are considering per unit depth to make our analysis simple. You don't need to write down the whole depth, maybe 4 inch, 5 inch. Right now, we will just write down as a 4 per unit depth. Agreed. So stress times the height minus, this is on the left hand side, negative side. Okay, this is my negative side. Okay, and this is times h. So this stress is, if you consider this is the area for this stress, this is the area per unit depth. You see, if I go back, I'm just making a figure more complex, but it's not that complex. This stress is on this plane. You understood that point? And this pressure is acting on this side. How about tau f? This tau f. You see my point? If you closely look, tau f is to the right. So can I write down 2 tau f, shear stress? I would say this is the known as the friction stress. We have to overcome the friction force. When the forging force, the ram, it hits the forging, there is a friction present. And then multiply by dx. This is the dx. You see, this is small dx. You understood that point? The friction force equals to mu times p times 2 tau flow. It is over here as well as at the bottom. If you multiply it, it's cancelled out. So d sigma x times the height equals to negative 2 tau flow. I would say not flow, but tau friction, because this is a friction. Make this equation as equation number 1. You know, in more stress circle, what happens, the x, look, let me show you the slide, next slide here. So if I draw the more stress circle here, then you can see this is my stress here in the x direction, stress here in the y direction, pressure. This is my y direction, this is my x direction. Okay, now this is my principal stresses where there is no shear stress. Okay, and this y-axis tells me the shear stress. And if this radius, if you at this point, what is this point? The average. This point is the average point, which is equals to, if you reach at this pressure, at this stress value, average stress value, then you will start shearing the material. That's what the Tresca yield criteria is. Suppose average stress equals to K value. Sometime you will see average stress equals to K value, and that is equal to 2K, which is the tau flow. Shear stress to flow the material, Tresca says. And now you will see sigma x plus p equals to 2 times k. This 2 coming from the average, denominator is the average, right? You see my point? And that is equal to von Mises. Von Mises says if distortion energy, since this is a plane strain, so we are doing this work. So if the distortion energy reaches this value, then material will start flowing. You see, this is more stress circle. And have you taken this strength of material class before? Do you know more stress circle? But one axis is x-axis, the other one is y-axis. You draw maximum minimum stresses, or and then you get the radius is the shear stress. Now some analysis. Let me show you the algebra or calculus 1. Have you taken calculus 1 and 2? That's good. So now differentiating and substituting the Mohr circle equation. This is our Mohr circle equation. As I mentioned, the average, you see, the average stress is this one. So if you differentiate, and then you get this value, and you get, so from noting that the friction force, friction stress equals to mu times P, and in the end you will get this equation. Now from this equation you have to do certain uh, limits, apply some limits of integration. If you integrate it on both sides from the starting flow stress, this is the starting point. Minimum it should be, yielding point is 2K. Okay, from the, and the highest pressure, you understood my point. So if the flow stress, which is the starting of the plastically deformation, you see, it should have at least minimum 2K stress applied pressure. If this is below 2K, it will not start deforming. It should have 2K, and then to the larger pressure, this P upper limit is higher than 2K. You understood that point? And then on the left hand side, it goes from 0 to X. You will ask me, Professor, what is 0? So I'll tell you, suppose this is my starting point. This is my 0 Y origin. Agreed. So now it should have at least 2K stress. But let me show you the figure. If you integrate it, sliding region. Now you will see two words in our forging analysis. One is sliding region, and the other word is sticking region. And you will see, let me show you a brief. This is a center line, okay, center line. And now look over here, suppose the pressure over here is 2K, and over here it increases here. Up until center line, you will have the maximum forging pressure in the center of the forging piece. You will have minimum forging pressure at the outer surface of the forging. But that minimum should be at least 2K, that pressure, in order to start yielding. You understood that? So now you will understand one thing, that what is the sliding region and what is the sticking region. You will see in the end that this might be sliding up until xk, from 0 to xk, and the other one after the center line is a mirror image. So don't worry, I'm just focusing on the left hand side of the forging piece. Left hand, the deformation process. Once you do the deformation, understand the slab analysis on the left hand side, you just multiply by 2. I will show you, it's a mirror image. The right hand side is the same thing. So let me show you, if you integrate it, can you integrate this portion like this? Ln Px over 2K. 2 mu over h is constant, and the integral of dx is just x. You agree with me? So x minus 0. So you just write down x. Now, how do you eliminate ln? You take the exponent on both sides. So can I write down p over 2k equals to exponent 2 mu over h times x? This is constant times x. This is another equation which will be useful for our analysis. So you understood this 2K is also the deformation pressure, and P is also the applied pressure. So if I write down the instantaneous pressure equation, this is my instantaneous pressure equation, okay? 2 mu over H times X, and this 2K, according to von Mises, it should be equal to 1.15 times sigma flow, or the yielding stress. This is our instantaneous pressure at any x value. And then the friction stress is mu times the normal force, normal pressure. This is my normal pressure, and the normal pressure upward, and sigma flow is to the right side, because this is center line. This is on the left hand side. Material is flowing to the left hand side. So shear stress force friction pressure is to the right hand side. Let me show you. If flow stress is greater than K value, or sticking, if this is less than, if tau friction is less than K value, is sliding. In the slide, let me explain to you. This is just the integration work, and then average pressure. After you do the instantaneous, this is the formula for instantaneous pressure. But for average pressure, you do this formula. Please note down this formula in your formula sheet. This is the average pressure, forging pressure. For sliding, there will be another forging pressure. So what is the average force? So you will see, if I ask you what is the average forging force for sliding region, there are two types of forces. Total force would be equal to F sliding region plus F sticking region. Now, forging force for the sliding case, all this P average, P average times xk times the depth, and you will multiply by 2. This 2 is coming because it is on both sides, okay? Xk times the depth times 2. So this formula, you need it for your homework problems. Now, if suppose the whole case is sliding, assuming the whole is sliding surface. So what will happen? So average for all approximation, there is no sticking. Friction force is less than the K value. So in this case, what will happen, that you assume that from 0 to the center line, W by 2 is the width over half of the width, which is the center line, all sliding. And then in that case, you will use this term P average times, so this is my P average, and multiplied by the same area. Do you see? The area is total width, not W by 2. but total width times the depth. This is a forcing force when you are assuming that the friction force is less than the uh, flow, the K value. Let me show you over here. If the friction if the friction force is greater, or sorry, less than the flow stress, this is all sliding. If it is greater, then this is all sticking. You try to understand this is sticking inside and sliding outside. But what if you assume that everywhere the friction force, therefore we put some lubricant. When you are doing forging, lubrication is good to increase the ductility process, and increase reduce the forging force, I would say, like uh, friction is reduced when you have a sticking and sliding case. So please note down, this is the boundary line. This formula is very important to find out where is the sticking and sliding region. This line, you see, this is my 0 to xk. This is my xk. This is my center line, which is W by 2. I will say W by 2. You see my point, guys? So this xk. So this is the first thing which I will do when I see the question, where is it sticking or the whole sliding, and how will you use this formula? So make sure one thing I want to mention here. This is an instantaneous height, or I would say the final height. This h is equals to a final height, h final. Suppose I say from 1 inch to reduce it to 0.25 of an inch. So you will not use 1 inch. You will use 0.25 height. Final depth of the forging in this formula. And mu is the coefficient of friction. You understood that point? And if you are having both sticking and sliding case, so then in the end you will find out the total for sticking region at x equals to xk, and pxk equals to k over mu. This k equals to mu times p, and this is the same formula I just mentioned here. This is the form. Now the remaining portion, it is up until xk it was sliding, but now from xk to half of the width, which is the center line, it is all sticking. So this is the instantaneous pressure of the sticking region. But how you have to take the average pressure. Okay, average pressure is how much? This is the formula for finding the average pressure. Dimensionless. And then after doing some calculus, I want to jump to the final formula for the average force. So this was my average pressure here, average pressure of the sticking region. You see, divided by the center line minus the xk. Up until from 0 to xk is the sliding region, and half of the width minus xk is all sticking. You see my point, guys? So now let me show you over here. You multiply this by the average, the area. Area is now total width minus 2 times xk, because on both sides, 2 times. Suppose it is 0.25, you multiply by 2. Both sides is 0.25, and then multiply by the total depth. So this is our lengthy formula. So you should be good in keeping the track of the calculations in such a, this has a lengthy calculations. So this formula you need for finding the, this is the for the sticking region, the force of the sticking region, and this is the force of the sliding region. Yes, this is the force formula, forging force of the sliding region. So if I grab it here again to show you this formula and the difference between this formula and this formula, you see these two formula. This only the difference is, look over here, the depth is multiplied by the width from 0 to 2xk. Over here, the width is w minus 2xk. W is the final width. And I'm not expecting that you memorize these formulae. I will provide you, but I will suggest you are allowed to bring one formula sheet on Thursday for the test. This will be a test question. One question will be from casting, one from forging, one from drawing, which I will teach you on Thursday. Okay, now look, the friction force or increases from outside to the center line. The friction increases. If xk is very, very small, very small, then W we can assume all sticking. We had a all sliding assumption, but now we are assuming all sticking. In that case, this is the formula for the P average. This formula is for all sticking pressure, average pressure for all sticking case, and then multiply by the width, the complete width of the forging piece, which is this one multiply. This is my area under the forging pressure, forging force. Please note this is assumption that we have all sticking. And there is another case when we have assumed that all sliding. This is my approximate. This is, so look over here. This is my all sliding approximation. I'm just bringing it to you again and again that you will identify whether the forging is all sticking or all sliding. This is the formula for all sliding. And when you are in between sliding and sticking, then you have to find out the total force, which is the combination of sticking and sliding. You should be ready to use calculator a lot. Please bring your two calculators. If one battery goes down, you should have another standby calculator in the exam. And this is the first lecture. You remember, this is the power law for the plastic deformation. Sigma equals to K times epsilon. Yielding. Y stands for yielding. Sigma flow is also the yielding stress. Epsilon ln hi over. This is a true strain. And what is this? This is the formula when you have hot forging. And what I mean by hot forging, if it is greater than half of the melting point of the metal, sometimes we have to make it hot to reduce the friction and reduce the forging force. It will be very fast to forge it. You see red hot in the last lecture. You remember last lecture? Hot forging. We need to understand that high temperature helps us in, yes, this is our, when the temperature is higher than half of the, I would say half, here it is saying 60% of the melting point, but you can use this formula. Sigma flow should be strain, we call this sigma, this power law for temperature is very, very important. Cold forging and hot forging, you understood the difference between the temperature. If it is less than half of the melting point, it's known as cold forging. If it is higher, then you will, less than, you will use this formula. If it is higher than half of the melting point, you will use the other stress formula. You see, they are doing hot forging here. Hot forging. But anyways, I just want to mention here. So with that, let's do one problem. Open your notebook and let's solve this problem together. These are the formulae only. Okay, I will show you how to apply these formulae in order to find out the forces. So this is a lead piece, 1 inch by 1 inch by 36 inch is the depth. Okay, so I'm gonna write down the initial height. If I consider like this one, if I consider this is my front face, this is my depth. Okay, this is my depth. Okay, and this depth is how much? 36 inches. Okay, look, 36 inches, and this is my 1 inch width and 1 inch height. Initial height is equal to 1 inch, and the initial width equals to 1 inch, and the final height is quarter an inch, and and the mu, coefficient of friction, is 0.25. Show the effect of friction on the total forging force. Total force. Now let me ask you, how do you identify? Is it our before I do the analysis, I want to show you volume is constant. Volume before the forging and after the forging is constant, and that is a very helpful fact. It can help me to find out the final width. Look over here, can I write down initial width, initial height, initial width times the depth. This is the total volume before the forging force or before the impact and after the impact. You see, we do the momentum equations like this. So I'm just little, you have studied dynamics. So okay, after the impact, this is the form. So this is the volume. Depth is not changing at all. Forging is does not change the depth. It only changes height and width. Depth remains per unit, I would say. This constant. So can you find out the final width, initial height? Open your calculators and help your professor. 1 times 1 divided by 0.25. 4 inches. So the final width of the forging, it increases. You see, and it makes sense to me because you are having a forging, it increases from 1 inch, from 1 inch to 4 inch, and the height is reduced to 1/4 of an inch. You see my point, guys? So it just, you can imagine in your head how everything is going on. Imagine this is a forging force and the billet is reducing its height and depth, depth remains unchanged, and the width increases. And now let's find out the sticking and sliding region. Can you go back to this formula? I want to highlight this formula. I think I mentioned, yeah, this formula. This formula is very important, which is the boundary line of sticking and sliding region. Can you calculate that? Make sure this is the final height, okay? So that you will not confuse. 2 times, what is mu? 0.25. Agreed? Are you going to help your professor? Who will tell me the answer? I'm going to write down, but you will match it with me, okay? Final height is 0.25. In my uh, calculation, I think this is 0.35 inches. Do you get this answer? Let me know. Open your calculators and help your professor. You got it? He got it? She got it? That's good. Any other verification? Yes? Yes? He says yes. He says yes. She says yes. Pamela says yes. Good job, guys. Now let me tell you one thing. Look, you will tell me this is the final center line is this is my W by 2. Okay, this is my W by 2. 0 to 0 to 0.35. 0 is the outer boundary up until center line, which is half of the width. And you will tell me is the same thing 0.35 on the this side. From here to here is W by 2 here, which is 2 inches. You will tell me what formula should I use, sticking and sliding, or approximate it to all sticking or all sliding? What do you suggest your professor? In order to find out force, this region up until this region is all sliding. And this is the same on the mirror image on the other side. Do you think we can approximate to be all sticking, or should we have mixture, combination of sliding and sticking forging force? What do you suggest me? I would say separate. So do the forging force for sliding, because 0.35 is still not negligibly small. We can do that. Let's do apply. Can you help me? Sliding region. Okay. What is my, I'm going to show you the formula for the pressure of the sliding region. Sliding region, if I go back, yes, this is, look, this slide. This slide tells me this is the, let's apply this formula. So I'm going to use this formula for the sliding case. 1.15 sigma flow and what is sigma flow? It is 1000 psi. Yielding stress is how much? 1000. So sigma flow is the yielding stress, and this is exponent e to the power 2.25 X is algebraically written because the question is effects of friction for the whole region. So you have to see, in the end, you will see one thing. You will see the effect of friction like this, forcing forcing. You see my point? The one which I drew over here, let me show you. You will see like a friction hill. Friction keeps on increasing and decreasing. And so I want to show you, in the end you will see. So let's keep algebraically here, 0.25 times divided by the final height, which is how much? 0.25. This is cancelled by this is, so what is this? 1000 multiplied by 1.15 e to the power 2x. So this is, if you plug it in your MATLAB, then you can find out the pressure at every location up until the sliding value 0.35 x in our case, up until xk, we call it xk. You see my point, guys? Try to understand this. So up until this point, this is 0.35. And after 0.35, it's sticking pressure. It's not this formula. It's a different formula. You have to subtract 0.35 from W by 2. You see, this will be the side minus 0.35 for the sticking pressure. You will see it now. I'm going to show you. Let me show you for sticking. Let me bring my sample here. Is this slide clear? First of all, you will find out the transition line. Where is sticking and sliding boundary? Is this sliding instantaneous pressure clear? And then comes the sticking. Now you will apply the other formula for sticking region. I will say when you go home, redo this by your own hand. Use this formula sheet, make a formula sheet. This is the formula for the sticking pressure. And now the next part is find the force. Look over here. This is what I want to see in your, it is difficult for you to find out at every location. You see, forcing pressure, or in the end, forcing force is increasing. Have you understood this question? So if you know Px of the sticking and Px for the sliding, can you find out the force? So because look, area sliding. What is area sliding? It is 0.35. Look, it is 0.35 times 2. Times the depth. And if you don't want to consider the depth, it's okay. You can mention, Professor, this is the per unit depth. In our handouts, to make the analysis simpler, they have assumed per unit depth. You don't have to multiply by the 36-inch. But what is area sticking? You will tell me. Area sticking. Look, this is my forging piece. This is my 0.35. This is my W by 2. This is my 0.35. So I'm going to write down area sticking equals to 2 times W by 2 minus 0.35. You understood this point? So can I write down like this? If you distribute W2 inside, W minus 2 times 0.35. Agreed? It's about 3.31 inches per unit depth, I would mention, so that you will not can get confused. So, so you multiply by this area. So let me show you the next slide here. Friction here. The question is up until here is finished. But let's find out the average force. This is the instantaneous force, but what is the average force? You have to solve it separately for sliding and sticking. You already found the average sliding here and average sticking here multiplied by area. So let me show you the final answer here. Yes. These formulae I already mentioned earlier. Is the formula is for average pressure. When you see the denominator is W2, W over 2 minus XK, this is our stick. You can see, look over here, when the denominator is from XK to 0, is sliding. And from W by 2 till XK, this is sticking. So this is the formula. So you have to use this formula for sticking forcing force and the other formula for sliding. And this is my area, sticking and sliding. Only these type of questions, if you understood this example, I assure you you will see similar problem in your exam. You have to at least be comfortable solving the forcing force required to change this dimension, deform it. Now there is another assumption. After this, there's another question. If you assume everything is sticking, then this is the total force. You see, I showed you this formula earlier. When you are assuming that the whole uh, sticking forging is sticking. You see my point, guys? This is the assumption. You can assume this is my sticking. So let me show you. Over here, what we are seeing here is the same formula. You see my point, guys? So it's the same formula. When we are assuming that we neglect 0.35 and we assume the whole uh, half of the width is sticking, means the whole forging is sticking. How much force you found? You look, you have to apply extra 20 tons of force when you assume that the all forging is sticking because you are overcoming the friction force. And when you do the transition between xk and w by 2, you reduce 20 tons of force. That's a lot of force. If you are having a forging press, you must be capable enough the forging press to provide at least that much tonnage, 414 tonnage for covering the sticking, to be more conservative rather than being at the sliding. When you are designing a forging press, you should be having a little bit more factor of safety. That much force should be higher than the calculated force. As an as a mechanical engineer, manufacturing, you should know this formula. And if you understood, have you understood how to apply this formula? Can you redo this at home today or tomorrow before the meeting? We are meeting again on Thursday, but during the weekend, I know you are busy. Other classes. How many of you are taking more than two classes? Wow, the whole class. You will graduate like this. You are determined, focused. You are not making going Dunkin' Donut to make money. People go over there, Home Depot, Dunkin' to make money during the summer, relax. But you want to finish, make more money. If I were you, I would do the same. Graduate fast, focus on one thing, and then you will have the fruit of this patience. You will eat it. Is this just abstract? Okay, now I'm just telling you that if you have different, if I change the mu value from 0 to zero point 0.5, then it changes the forging force up until 25,000 pound force per inch. But this is just a graph which you are not required to do the graph in our exam. This requires some MATLAB formulation. You just make a vector of mu into the script and just find out the force. You know how to do that in MATLAB. You are about to graduate, so you know very well about MATLAB. You see, this is the table. In the end, you will see force of friction, coefficient of friction increases, and the maximum force goes from 4600 psi to 23,000 psi. The effect of friction is very important. That's why we put lubricant. This is all sliding. You see, half of the width is 2 inches, all sliding, and this is transition, and this is all sticking. And then it's another chart here showing you from 0 to 23,000 psi. So I want to tell you that we have finished the analysis, that you should be comfortable in finding the forging force using this formula. I would look, if you understood this question, I'm gonna share with you at least two more homework problems, two or three maximum, because they are lengthy problems. Okay, but if you practice those, you will see similar question in your test. Another analysis is for the forging which is not rectangular but a round forging. This is for learning purpose. I will not give you a question from the, because it's little more complex. But I want to show you, at least for learning purpose, okay? What if you have some students, they really want to learn. And I have given you these slides, okay? When you have a forging of a cylinder, how will you find out sticking, sliding, and do the forging force of a cylindrical forging piece? You want to see the analysis? Look, it's not that lengthy, but it requires some uh, more formulation. This is a cylindrical forging piece. We want to forge it And when we forge it, you see this much is sticky. The concept is same. Inside near the center line is all sticky, and the forging pressure increases outside the transition line. This may be transition line. So this is the mu p friction force, mu times the normal uh, force, which is normal pressure. At least we are doing this for the pressure. So this is the um, forces, all the force in the radial direction, doing the analysis. And I want to show you the more stress circle, the shear stress. So here you can integrate it to find out the transition point. This is our instantaneous pressure, average pressure. Everyone has done calculus 1 and 2. They can practice symbolical. This is all symbolic calculus. And this is a forging force for all sliding, forging force for a cylindrical piece. This force formula, you should know how to. It's just a formula. If I give you the parameters, you should be able to find out the forging force of a cylindrical piece. Is it difficult? No, it's not difficult. I think I should give you a similar question, at least in the homework, maybe not in the exam. What do you suggest? Homework at least for practice, right? Or in the exam too? Formula in the exam too? Yes, you say exam? The cylindrical forging lengthy formula? She says no. You you say Arden? He says so I'm not giving, but for the homework, at least for just to practice. He says yes. Okay, that's good. So when you know the forging average pressure, you just multiply by this for all sliding approximation. This is the formula. Here we don't consider x but only the radius. Okay, r stands for the radius. And now transition between sticking and sliding. This is rk. You have to use this formula in order to see whether it can be all sticking or in the middle. Prescott criteria. So I'm going to show you this formula. Yes. So I'm skipping some slides here for your review later. It's just the calculus, and this is the formula. This is the final formula, assuming that all the sticking region r small r sub k means that transition radius. You understood that point? And then it's a combination. The method is same. The procedure is same, but only the formulas are different. You see the same procedure. Now comes the strain hardening formula here. So this is the power law or the stress law here. For Tresca says the yielding stress equals to K times epsilon to the power n, which is 2 times the flow, tau flow. And for hot, two-top flow is equal to y, which is this form. Average force pressure. With that, we have finished this sliding and sticking region for the cylindrical and for the flat rectangular piece.